Hello everyone and welcome to our webinar named as Leverage Databricks Predictive Analytics to Enhance Power and Energy Infrastructure. In this webinar, we would be focusing on Databricks and we will be using a case study in energy and power sector. Let me introduce myself. My name is Hassan Sherwani. I'm working as practice head for Royal Cyber in Data Analytics Department. I have around 14 years of experience in this domain. Mainly, I work with machine learning models and data engineering pipeline. I have my colleagues Zishan, Arif, and Moaz with me. Zishan, could you introduce yourself, please?
Hi everyone. Thank you, Hassan, for giving me an opportunity to speak about this project. My name is Ishan Arif. I have around 17 plus years of experience in data engineering. I have worked on projects of all shapes and sizes, and I also have experience in Databricks and Spark. Now I would like to introduce my colleague Moaz. Moaz, can you continue, please?
Yes, thank you, Zishan. Hello, everyone. My name is Moaz Ahmed, and I am a data scientist working for the past 3 years at Royal Cyber. Throughout my journey, I have been in close proximity with different domains that include data engineering, generative AI, and data governance. For the past few months, I have been lucky enough to operate with Databricks and observe its multiple features. And now we shall be presenting many of those features in this demo.
Thank you, Moaz.
Back to you, Hassan.
Thank you. So moving forward, agenda is that first up we would talk about Royal Cyber. What are we, what we do, what are our services? Then we would come up to our introduction. First up, we would introduce you to Data Intelligence Platform, which is an amazing feature and a very new one for Databricks. Afterwards, we would give you a brief overview of governance infrastructure and how Unity Catalog comes in place with this bigger platform approach. Afterwards, we would share a case study that we have recently worked with our clients and what we learned from that case study. And finally, there will be a Q&A session where we would appreciate your participation. Starting off with Royal Cyber. We are a very mature organization, 20 plus experience in this domain for servicing and consultancy. Our presence is around the globe. We have our head office in Naperville, Chicago region. We have other subsidiaries in Mexico, Canada. For offshore, we have a KSA, that is Saudi Arabia, India, Pakistan, Australia, and New Zealand. So you can see that we start from one edge of world and we end at the other part of it. So our presence is global and we really take pride in our employers because our consultants are certified, very reliable and highly skilled. We are gold partner with Microsoft and we have other partners. So for example, with Databricks and Snowflake, we have a very strong and long partnerships with which we also do data engineering, data science projects. Moving forward about data analytics practice, we have four streams in this practice. First up is data engineering. And by the way, our webinar is somewhat close to this practice. In this practice, we work with business processes, our automation, our data strategies, its securities, warehouse, and ETL pipelines. In addition to that, we take care of our governance as well, that our data is compliant and security is there. Afterwards, we have machine learning solution. This is where we work with predictive models. This practice or this stream includes our feature engineering, our data processing, our model building, then model selection, and then of course, hyperparameter tuning. Afterwards, there is a new domain which is coming uprising is generative AI. Over there, we create a differentiation between our predictive and our generative models, where we work mostly with massive data sets which are unstructured, such as text, images, and media like video data. And in this stream, we are working for recent upgrades of transformers such as ChatGTP and Llama Index. Fourth one is MLOps solution. Over here, we work what happens with our models once they get deployed, once our models become a product. What are the best practices that we do? So concepts like model drift, concept drift, or data drift are actually part of this solution. So out of all those practices in this webinar, we would actually speak how Databricks would actually make sense. Our focus would be around data engineering and data governance solution. That's where our Unity catalog, a platform, would come in place. So I would invite now to Zishan Arif to give you an overview of Databricks. What is it about? What its ecosystem is, and what this data intelligence platform is about. So, is this hype worth or not? So, over to you, Zishan. Thank you.
Thank you, Hassan, for giving me an opportunity to speak about predictive analytics using Databricks. As mentioned, for this webinar, we will be using Databricks to create a predictive analytics pipeline. But before we begin, I would like to take a few minutes of your time to discuss why Databricks. Databricks is a leading provider of the unified data analytics platform, enabling organizations to manage and harness the power of the data throughout its lifecycle, from data generation to data capture, from data cleansing to data quality management, from processing data of all shapes, types, and sizes to data reporting, visualization, and consumption for all kinds of data analytics like descriptive, predictive, and prescriptive analytics. Databricks is a data lakehouse which provides data management and reporting capabilities in the form of a data warehouse, but also for data of all types, shapes, and sizes, including fast growing structured, semi structured, and unstructured data like text files. Using the Databricks Unified Data Analytics platform, we have at the bottom a scalable cloud object storage layer which can store data in all formats like CSVs, Parquets, text, and media files in the form of blob storage. Then on top of the cloud storage, we have the Delta Lake layer, which uses schema on read to convert underlying objects into Delta tables, thereby enhancing the data lake to contain data warehousing capabilities like asset properties, including schema evolution and enforcement and transaction isolation, all the while keeping the processing and scalability features of a data lake intact. Databricks is also known as a data intelligence platform which sits on top of the Unity catalog layer to provide services like Databricks AI, Delta Live tables, workflows for data pipeline orchestrations, and a plain but powerful data warehouse. The data intelligence platform allows data analysts across the entire organization, from data engineers to data analysts to BI analysts to data scientists, ML engineers, and AI analysts, to utilize Databricks as a unified data analytics platform for their tasks. Rather than having different databases or different repositories for different types of analytics, Databricks allows for a unified data analytics repository. Now let's discuss Databricks data governance capability. Data governance involves rules and policies and its compliance for all phases of the data lifecycle, that is, from data generation to cleansing to storage and compliance to security and privacy policies to finally data archival. Databricks, under its Unity catalog and Delta Lake features, allows for comprehensive coverage of all data governance features and regulatory compliance requirements. Data governance forms the bedrock of organized data management, ensuring data consistency, security, and strategic alignment. As mentioned, Unity Catalog is the Databricks data governance implementation feature. Unity Catalog provides centralized role-based access control, auditing, lineage, and data discovery capabilities across Databricks workspaces. Here in this slide, you can see the various features of the Unity Catalog, from storage credential management to account user management, from audit logging to Metastore for basically storing information, metadata information about Delta Live tables, from Lineage Explorer to Data Explorer, and finally for access control management. All these features are part of the Unity catalog and are shipped out of the box with the Databricks environment at the click of a button. Now let's discuss the problem statement a bit and get into the details of the case study. An electric power producer generating electricity through wind turbines requires an inventory lead time of 2 months in case of wind turbine failure. This is due to the fact that the turbines have to be imported and the paperwork and shipment itself takes time. In case of turbine failure, the power producer has a couple of turbines available as backup. However, given the global warming and sporadic weather condition, it usually happens that multiple turbines fail together, leading to slowdown in power production due to unavailability of additional turbines. This catastrophic situation also leads to losses as the power producer is unable to operate on full capacity in peak time. So, in order to mitigate the risk of turbine failure, the power producer has opted for monitoring of turbines through the IoT sensor so that signs of wear and tear can be detected early for turbine replacement and repair. Further, the power producer uses predictive data analytics to predict turbine failure by analyzing large amounts of data being generated at a high rate by the IoT sensors. Given the size and speed with which the data is produced by the sensors, a big data, horizontally scalable, and cloud-based solutions like Databricks was the obvious choice. Predictive analytics, since it uses ML algorithms to do predictions on big data, requires both high compute and high storage capacity to be able to infer turbine performance for early failure signs in real time. Now let's have an overview of the predictive analytics pipeline, which does both inference as well as collect training data to minimize errors in prediction. The pipeline begins by ingesting raw sensor data into the landing zone. As new data files are generated, they are moved into the landing zone. The landing zone is actually Azure-based blob storage to store CSVs being generated by the sensors. This raw data from the bronze layer is processed and cleansed and moved into the incremental delta table being populated with hourly sensor data. From here, the hourly data is joined with the turbine master data file and fed into the ML model for predictive analytics. Finally, inventory master data and ML output is combined to produce the predictive analytics dashboard and displayed to management. So instead of reacting to failing equipment and fixing it once it fails, thereby slowing down or stopping the power production process, we can now use predictive analytics to proactively manage and enhance power production output.
Alright, so let's just start with our demo. As you could see, I have this catalog named as AWS underscore demo, and in that catalog I have this schema named as turbine data. This catalog is the Unity catalog and covers all the data governance capabilities that are provided by the Unity catalog. Similarly, within this schema, we can store tables, volumes, or even functions or entire ML models. We can give access to these type specific data within this catalog using the admin access. Right now, as you can see, our data engineer has only access to these volume. This volume contains the information about the raw data that is being fetched by the wind turbines directly. So we have in this volume we have information about historical turbine status, incoming data, parts, and turbine itself. And within these files we have some of them are JSON files while some of them are Parquet files. So what the data engineer is supposed to do is to read these files and make meaningful delta tables out of it, make necessary aggregations to those delta tables, and finally present the data in the form of a table that can be used for the training purposes for our machine learning engineer. So yeah, proceeding to the workspace of the data engineer, we see that this is the data ingestion process, and these are the notebooks which he has created. So I am simply going to click on run all, and while this happens, I'm going to explain the entire processes to you. So as you can see, the first thing is that we are using the Spark engine to read the data in the from the volume which is being stored in the catalog. Once the volume is stored, this is the historical data frame which tells us about the history of the historical data of the turbine corresponding to its turbine ID. So what we do is we save this historical DF in the form of a delta table and save it in this specific catalog and in this specific schema named as historical turbine status. So finally, once it is done, we read that table, and as you could see, this table is now being made. So this is what we repeat the entire processes with both the sensor data and the turbine data. So I am simply going to click run all at the moment. So this will again read, the first thing is reading the files of volume through Spark engine and then proceeding towards creating the delta table. And there you go, the creation of the delta tables is successful. And finally we have this turbine data. We are going to run all again, and this is going to again perform those things as commanded. So once it is done, we shall have a look at the output. So if we proceed towards our catalog now, and in the schema turbine data, we could see that there are now 3 tables along with the initial volume. So now these tables are being stored in the form of a delta format. So that means they are ACID compliant, they are properly structured, and they are scalable as well. So now the data ingestion processes have been completed, and now we shall move towards the data aggregation. So we have our sensor data, but since we are interested in the current status of a turbine, what we are going to do is that we are going to get hourly status of these sensor data. So in that way, we are going to create hourly timestamps of this sensor table, and we are going to store it in the form of a new table named as sensor hourly. So that is, once I run this, as you can see, the sensor hourly table is being has been successfully created. So now the last thing for the data engineer to do is to create the training data. So this right here is how he is going to create training data. So as you could see, initially you had the sensor hourly data and the historical turbine data along with the turbine table. So in that way we had access. Now combining these tables, we are going to have the historical status along with the hourly sensor data, and make a table that gives us the timely hour stamps on the overall turbine data, including the historical and the sensor data. So what I am going to do is I am going to run these entire notebooks again. So we create using the selected columns, we are going to create a table as an inner join that contains hourly timestamps of sensor hourly data and the historical turbine data in the form of something that can be trained by a ML engineer. So now, as all the things have been completed, I move to my catalog, and now if I look at this catalog, this you could see that these are the 5 tables which have been created now. This turbine training dataset is what is necessary for the ML engineer. He does not require any other details about the historical turbine status or any other thing, including the volume. So this turbine training dataset is what we will be transferring to our ML engineer. So now what we are going to do is that we are going to enter the workspace of our data scientist. The data engineer has done the job for us, and he has created a training dataset for us. So what we are going to do with the data scientist workspace is that we are going to use that training dataset to predict our anomalous sensors, and after that we are going to use some other tables to make things easy for our dashboard creation. So in that way we are going to do the entire thing for this workspace as a data scientist. So I move towards my catalog again, and in now this time, if I could see the schema turbine data, I have access to 3 tables. This is the turbine training dataset, the turbine itself, and sensor hourly. The turbine training dataset will be going to be used in order to perform the ML operations on it. We are going to implement an ML model on it, and we are going to predict the anomalous sensors. Once it is done, we are going to combine the output to turbine and sensor hourly data so that we can get the current status of the anomalous sensor within our domains. We also see an interesting thing out there is that this models right here. So this models, we are going to explain it shortly why this model is there at the moment. But as we could see here, the volume section is not visible right here. So that means we have given access to the data sciences of only the relevant data to him for the ML operations. So now what we are going to do is that we are going to use this turbine training dataset and implement an ML model. But we are not going to do that from scratch. Thanks to the ML flow capability provided by ML flow capability, which it provides in the form of an auto ML, we are going to use that auto ML to automate the process of the entire machine learning and predict our anomalous sensors without need to write the code from the scratch. So we are going to move to the experiments field right here. I'm going to create an AutoML experiment. We are going to give it as a classification type problem, and then we are going to give it our input dataset. So I'm going to turbine data, the turbine training dataset, and I'm going to give this table. And once I do that, since it is a classification problem, it is already giving me the columns which can be classified. For now, I'm going to classify abnormal sensors, and I'm going to name it as turbine maintenance. So now I'm going to start my AutoML experiment. The AutoML experiment is going to take a few minutes to start. Happens in an AutoML experiment is that it automatically implements multiple ML models on your dataset and predicts the amount of your target variable and gives you the list of ML models in the form of sorted accuracy of your desired metric. So in that way, you do not need to write anything from scratch. The AutoML is simply going to run an entire models and it is going to serve you those models. Once you have those models, you can register those models in the Unity catalog and use those models in the later run for the inference. And that is what brings back to the catalog, which there is a model which I have already stored because of the time constraints at the moment. We are going to get back to see the AutoML results in a while, but for now, what we are going to do is that we have one of our models stored in this, and we are going to allow the data scientist to use this model and give us the results. So this model takes the inputs which are in the form of these columns and it will give us the status of the anomalous sensor. So now we move to the model inference in the data scientist workspace, and now we are going to run this notebook. So I'm simply going to click run all, and while it is running, I'm going to explain the entire processes. So first thing, it loads this model which is named as turbine dbdemos underscore turbine maintenance, and it uses this model. It is using this model, it is going to create a prediction function. This predict maintenance UTF is now going to be implemented to create a table. So the table which we are going to finally create is named as turbine current status. And what happens is that it uses the hourly timestamps from the sensor hourly data and the turbine data. And based on their turbine IDs, it gives us the prediction and the status of the anomalous sensors. So in that way, we are going to not only predict the anomalous sensors, but then make a resultant table that is going to be very meaningful for us in order to make the necessary dashboards and findings. So this Spark job is running at the moment and it is going to take some time. So what happen in the meanwhile, what we can do is that we can move to the AutoML experiment and see what actually an AutoML experiment is. So I am going to this and I am going to this AutoML experiment, and this right here is the result of those AutoML experiments. And as you can see right here, I'm going to stop my experiment here and see what this experiment offers to me. So this right here tells me about the model which is named as peaceful mayor underscore 438, and this model gave me some very good accuracy for that. So if I look at the accuracy and I have sorted the entire thing from F1 score, this model is giving me 0.9849 F1 score. So that means that model is very comprehensive in itself. So what we do is that we register this model. We register this model in our Unity catalog, and once it is done, we can simply use this model. So we run these things and we register our model. And once we register our model, it is then stored in our catalog as described before. So now moving back to my workspace, and let me see if the notebook has run in itself or not. So yeah, as you can see here, the Spark notebook has completely run here, and it is going to give us a table named as turbine current status. So this turbine current status contains the hourly timestamps according to turbine IDs, description of the entire sensors and their standard deviations, percentile scores, and then finally it gives us a column in the form of a prediction. Here, as you can see in the topmost sensors, most of the sensor F were faulty sensors. Similarly, as we scroll through it, we see that sensor B is also of those faulty sensors among those sensors. And similarly, as you can see, we could see some sensor A's and mostly sensor B's and F right here. So in that way, we have a table through which we can make constructive and meaningful dashboards, and this table is brought to us thanks to the efforts provided by our data scientists. So if I go back to the catalog of our data scientists now, what I see is that I see 4 tables and I see a model right here. So in that way, the data scientist has helped us in predicting our anomalous sensors. So now it is up to our BI team to basically help us visualize these things and see what these results actually mean. We have our seen the Databricks engineer and our data scientists how they perform on our works on their desired workspaces. But now that it is time for the admin to see the overall progress, we have seen the governance part being implemented by specifically allotting specific data to our specific resources. So now what happens as an admin in the Databricks workspace? As an admin here, as you could see, when I go to the turbine data, I have access to all the tables right here, all the volumes here, and all the models. So the proper data distribution and efficient data and resource management is being implemented through this Unity catalog feature. I am assigning relevant data to relevant people now. Similarly, one interesting thing which I wanted to share as an admin right here is that I'm going to touch two main important features of governance which Databricks offers to us. The first feature is the grant provision. As you can see here in this table, I can allow permissions to specific users. I can allow permission based on 3-level structure. I can allow permission of the entire catalog, permission to use only schema, or even a single table. And even at that table, I can give read-only permission or modification permission. That entirely depends upon the admin. So yeah, that is something that governance features that Databricks Unity Catalog allows us. Similarly, one another important thing is the lineage feature. So as you can see here, the lineage tells us about the entire history and the necessary transformations applied on a table. So as an admin, if I could see here, this turbine training dataset, I click on this and it tells me how the entire transformations and necessary transformations were applied in order to make this turbine training dataset. This lineage graph is a very detailed graph, and it tells us not only about the datasets itself, but the columns within the datasets that have been changed. So for example, if you are running a pipeline and you are facing as an issue, you can simply use this lineage graph to backtrack the entire thing and get efficiently to your desired outcome. And now finally, as an admin, I'm not going to run the entire workspaces or entire notebooks by my data engineer and data scientist. So what I am going to do that is going to make me a meaningful dashboard right here is that I have created this job. So now this right here is a job that is an end-to-end process. So this end-to-end process job covers all the things that an admin is supposed to do. So what the admin is will do is that he's going to either trigger it manually or he is going to schedule it. Since it is a real time, since it is a webinar at the live webinar, I'm going to manually trigger the job and I'm going to share the results with you. But as you can see here in that job, we have this sensor bonds, historical data, sensor hourly data, turbine data, training dataset, inventory details, that is an addition, And finally, we have this turbine condition, and we are going to use the turbine condition to make a predictive dashboard. So these are the individual tasks which were assigned to in my job, and I am simply going to run this job. So we are going to let this run and we are going to wait for a while. So this job basically covers the notebooks and covers the paths of the notebooks to all the processes that have happened throughout until this entire predictive maintenance demo. So we have run the job and we are going to let it wait. So now as you could see that the job run was successful. So if now I click on this job run, this right here will bring me directly to my predictive dashboard. So going to my predictive dashboard here, so I have utilized all of those tables and we have created a predictive dashboard that is going to give me the entire results. So right now here, as you can see now, the total energy that is being generated by the current condition is 2567 megawatts, and because of that, we have had a revenue of $282,415 per hour. So, but the important factor is the active faulty train parts. So there are 121 active faulty parts within our turbines at the moment. And how is that faulty train part impacting those? There is this 7% impact to the revenue which those faulty sensors have made. And similarly, we have the entire details of all the sensors which are at the moment abnormal and where they are located along with their coordinates. And this tells this this donut graph right here tells you about most of the equipment which contains the faulty sensors. And here, as you can see, the anemometer contains 24% of the faulty sensors right here. Similarly, the electronic guidance system contains 13.8%, so on and so forth. Similarly, we have these coordinates of all the we have this all the coordinates of the wind turbines that are active, and finally we have some details about the inventory right here. So in the inventory we see that if there is an anemometer which is being provided, then it will take around 237 days to arrive. Similarly, for other equipment, there are different number of days that covers the supervision of those sensors, and that can help us in optimizing our processes and uh, making the necessary changes to our equipment. And similarly, there is one other thing. What if there are some changes to the data? Am I going to do then? We have similarly created a job. So let's suppose if we are dealing with real-time data that is continuously giving us the real-time changes in the sensors, and we want our dashboard to update at the real time. So what is going to happen is that this data updates job is there to do so. So this data update job has what tasks? It basically has this data alteration task, which alters the data coming from the sensors. Then it implements the model, and finally it gives us updated dashboard, but it doesn't make the dashboard right from the scratch. Rather, it gives the dashboard, it updates the dashboard on the real time. So we are going to let this job run and see how the changes are made in our real-time dashboard once this job is run. So as you could see that the job has been run successfully, and I'm going to implement this job and see the updated dashboard. So we haven't, it will direct us to the same dashboard right now, and it will show us the updated results. So after making a few changes in the data, we shall see the changes to the energy and the faults. So now, as you can see, the energy generation has been increased significantly and the revenue has also increased. And the active faulty strain parts haven't risen from that much, but they are still 13%, having 13% impact on the revenue. So using these results, we could see that if now the supervision of those faulty parts becomes even more necessary. So now to the business stakeholders and the investors right there, we see that we have built this entire dashboard on the platform of Databricks itself. So the part from the data science to data engineering, data governance, and the Lakeview dashboard finally, all of this has been implemented on the Databricks itself. We did not need to convert to a Power BI tool or any other specific tool. And that is where Databricks offers its versatility and its value to us. So if I could simply go at the back end, we see that there are simple queries running behind these SQL statements. So these are the queries running, and what they are using is that they are using the tables which we created in our catalog. Using those tables, we see that we have come to a conclusion and a great end result, which is our predictive dashboard. So yeah, that is it for the demo. And I hope you learned quite a lot of things from it and found some value of data governance and how it we are predictive maintenance we are applying predictive maintenance through the entire platform of Databricks itself.
Thank you, Moaz, for the detailed analysis of the code and other artifacts of the project. So now we'll talk about the outcomes of the project and what we have achieved by using Databricks for the project as a platform, as well as what lessons did we learn out of performing this proof of concept activity for this webinar. So for the outcomes, the first thing to notice is the improved scalability, performance, and agility to handle growing data volumes and complex analytics. As mentioned, Databricks is a unified data analytics platform, and it is horizontally scalable due to its architecture and allows for massively increasing data volumes and compute expectations. Enhanced data accessibility and collaboration for faster and more informed decision making. As we talked about Databricks' Unity Catalog, we also mentioned that the Unity Catalog not only does data governance but also enables data accessibility and collaboration due to the fact that multiple levels of security and role-based access control is enabled in Databricks, which allows for data engineers, BI analysts, data scientists, ML engineers, and AI analysts to work together within a single platform to produce outputs for whatever repositories they are working on, repositories and datasets they are working on. Optimized resource and data allocation leading to reduction in data fragments and silos. As mentioned, the Unity Catalog and the Databricks data intelligence platforms enables data allocation leading to reduction in data fragment and silos. It is not like whether a data engineer is unaware of the data set which they produce and which is being used downstream by, let's say, a BI analyst or a data scientist. So everyone within the organization knows where and what data is present through the use of Unity Catalog, because it has also the feature of cataloging all the data sets available within the organization and for the organization. Improve data security and compliance through Unity Catalog security and governance features. As mentioned, Unity Catalog's role-based access control enables security features and governance capabilities which are sufficient for large and growing organizations' needs. Not only does it enable the reduction of data silos, and the data cataloging allows for access and reduction in data fragments, it also enables features and governance capabilities for security and compliance. real-world predictive maintenance for necessary equipment and turbines. And finally, from a functional and business perspective, this project is a proof of concept which highlights how Databricks can be used for real-world predictive maintenance for necessary equipment and wind turbine procurement. As the vendor or as the business or power producer uses uh, the predictive analytics pipelines and framework and gets real time reporting on which turbines are expected to fail in the near future, they can manage their procurement and inventory process and ensure that they proactively can order turbines before they fail and are able to manage the production of electricity in their given power plant. Finally, let's discuss the lesson learned for the project. Databricks platform can be comprehensively used as a single platform for data and AI solutions. As we have been mentioning since the beginning that Databricks is a unified data analytics platform, and we also demonstrated that capability through the use of the Unity catalog, through the use of elimination of data silos and elimination of data fragments, through the use of multiple teams collaborating together on multiple data sets together in real time. So we have demonstrated how Databricks can be used to comprehensively reduce data silos and data fragments and enable a single data platform for data analytics and AI solutions. Unity Catalog offers a wide range of governance capabilities, including grants, lineage, resource management, hierarchical level access, etc. As mentioned, the Unity catalog in Databricks offers a wide range of governance capabilities. It also provides a capability of data lineage where we can even track which columns from which data sets are being sourced into which pipelines and being produced as output in which target data sets. This enables users to keep track of how their data is moving across the data pipelines and how their data sets which they are using are currently being generated or produced by source data being fed into the Databricks landing in area. The detection of faulty parts of turbines could prove to be a valuable asset in both the predictive maintenance and inventory optimization processes in the energy and power sector. As we discussed, that predictive maintenance is all about proactive management, because with predictive maintenance we know we are able to figure out which parts or which turbines or which areas of the power production plant are expected to fail when. So if we know when a given turbine is expected to fail, for example, we can proactively procure the turbine rather than waiting for the turbine to fail and then reactively running after firefighting in a firefighting mode and trying to procure a turbine once it has failed. Because once the turbine fails and given the 2 month inventory lag period, this could lead to severe reduction in production of electricity, which could lead to losses to both the companies as well as the entire electricity grid. Efficient collaboration of different members of an AI team on a single and comprehensive data platform to create an end-to-end solutions without any data losses, data silos, or data fragments. As mentioned, that the whole AI team or the whole data engineering and data science team can work together and collaborate effectively with each other in order to produce the final output of this predictive analytics pipeline, and enable the business to work and enable the business to be able to use that predictive maintenance pipeline for proactive decision making. So rather than the data engineers not having access to the data science environment, or AI engineers going back and forth between data engineers and data scientists to figure out where and what issues are being faced in the production or coding of these data pipelines. So when everything is in a single place, collaborations becomes easy, and the turnaround time or the throughput time of analytics is reduced. I hope you like this webinar, and we hope that we were able to demonstrate effectively how Databricks can be used for for uh, how Databricks can be used for predictive analytics and data management to enable proactive decision making in businesses, especially in the energy and power production sector. Thank you very much.